So what does it say up there? It says, I tried to spell smile. Triangle SMI is similar to triangle ILE. Solve for X. So the only thing you really have to be aware of on a problem like this is making sure you match up the corresponding sides correctly. Remember, in similar polygons or triangles for that matter, angles are congruent, sides are proportional. So that's how you're going to approach this problem. Let's just pick a number, any number. And let's see which side corresponds to it. So IM is listed third, second, and EL is listed third, second. So the 80 goes with the 60. 80 is to 60 as, now it's easy to follow through because we know which ones kind of go together after that. 80 is to 60 as x plus 32 is to x. We do our favorite thing in the world in this unit, which is to cross multiply. 80x equals, we have to be careful and make sure we distribute 60x plus, anyone have that number for me? 60 times 32. Yep, I ran out of room. All right, we'll subtract 60x from both sides. 20x equals 1,920. Take that and divide by 20. What are we getting? What is x? Those are the directions. Solve for x. Very nice. 96. Your quiz today will ask for scale factor quite a bit. What would be the scale factor from triangle SMI to triangle ILE? What would the scale factor be? If this is my first, and this is my second, from SMI to ILE. So we put second over first, right? So it'd be 3/4. Notice from SMI to ILE, we're getting smaller. So our scale factor has to be less than 1. Yeah, just keep in mind, if it's getting larger, your scale factor will be greater than 1. If it's getting smaller, your scale factor will be less than 1. And that's how you'll know on the quiz whether you put the second over the first correctly or not. So 3/4 would be the scale factor from here to here. All right, getting small. Last night's homework, triangle proportionality theorem. Honestly, you used all sorts of theorems on this homework. You didn't just use the triangle proportionality theorem. On a lot of those, to find one of the variables, you could have used the theorem, but to find the other variables, you couldn't use the theorem. So we have to be really careful about that. Go ahead and check your answers and let me know which ones to solve. All right, first things first, let's start with number 1. In number 1, to find y, we will use the triangle proportionality theorem. So I'm going to go through this quickly. 4 is to 8 as 3 is to y. That is a basic application of the triangle proportionality theorem. You cross multiply, you find y. So you do 8 times 3 divided by 4, or you just see that the scale factor is 2 and you know that it's 6. Anyways, y is 6. Now, to find x is in a completely different story. I don't say 4 is to 8 as x is to 21. I do not use that because the triangle proportionality theorem does not include those parallel sides. That's not part of the theorem. So you would say 4 is to something as x is to 21. We don't want to use a partial side because x is a whole side and 21 is a whole side. We don't want to say whole over partial equals whole over whole. I'm not allowed to do that. So instead, we need to add 4 plus 8. We need to find this whole side, which is 12. Do you see how that works and why that's different? It's different because it is the parallel sides. It's not the side being broken up into proportional pieces. Those are all pieces. This one's not. So 4 times 21 divided by 12. 7. X is 7. All right, let's look at number 8. Number 8. This one, you could use the theorem because that parallel line is cutting those sides into portions, into pieces. The problem is, on this side, you don't know either of the pieces. I don't know this and I don't know this. So I can't set up a proportion when I have two unknowns. So we're actually going to solve for this just using similar triangles, not using our fancy new theorem really at all. Watch what I'm going to do. I'm going to say 6 is to something as, I'm going to call this y, as y is to 24. See how I did as y is to 24? So I would do 6 is to, I would need 24's counterpart. I would need the corresponding side of 24, which would be 16. Take a look at that and make sure that makes sense to you. 6 is to 16 as y is to 24. I added a variable because we can't start off by finding x. Are we okay with that? 6 times 24 divided by 16. And we get 9. This is 9, and then to find x, we would just do 24 minus 9. Number 10, all these word problems, we're actually going to be talking a lot about word problems today. So you've already seen them, but that's what today's lesson is. We want to find the distance across the river. So once again, unfortunately, even though this is called the triangle proportionality theorem, you're not going to use that theorem on this triangle. You're just going to use similar triangles. You're going to use similarity. So I could say 75 is to 100, because those are corresponding sides, as x is to, and here I have to be careful. 75 and x, those go together, right? Those are parts of that same triangle. Now, 100, that whole side is going to go with this whole side. So how could I name that whole side? It's not x, it's not 25. What is it? Very good. So it's really important that we call this x plus 25. Okay? And now we're back to kind of what we did in the warm-up. You're going to cross multiply, you're going to distribute that 75, and you'll solve for x, okay? I'm not going to go through the steps. I think setting it up was the hardest part. I'll do 12 real quick because I love 12 because it's actually an application of what we learned yesterday. Number 12, we've got this, these are parallel, which is really important. To use that theorem, you've got to have those segments be parallel. So those are parallel. That means that EB has split my triangle's sides into proportional parts. So I can literally just use the theorem we learned yesterday. 300 is to 620 as 240 is to x, where the distance across the river is x. And cross multiply and divide. So number 12, nothing tricky about that, basic application of yesterday's theorem. Number 13, there are 3 triangles here. We only want to look at 2 triangles at a time. We just want to look at 2 triangles at a time. So in number 13, I'm going to look at this triangle, and I'm going to compare it to this triangle. We're just going to set up a proportion. So I could say 2 is to 5 as 1 is to question mark. Take a look at what I wrote and make sure you understand what I wrote. Where did I get the 5? Yes, Kendra. 2 is to 5, good, as 1 is to question mark. Hopefully everyone is seeing what I'm doing here, and you're never going to put 2 is to 3 as 1 is to x. That would for sure guarantee you the wrong answer. So you cross multiply and you get 2.5, right? Or 5 halves. Now we're going to use this small triangle again. Never use information that you found yourself. Use the information given. We're going to use that small triangle, and then we're going to look at the large triangle. We're going to ignore that middle triangle. So I'm going to say 2 is to 10 as 1 is to question mark. You know where I got the 10. I did 2 plus 3 plus 5. 2 is to 10 as 1 is to question mark. Yep, cross multiply and you get 5. Okay? Today's lesson is called Can You Measure It? Here's a little there's like a mini history lesson in today's lesson, but I think it's cool to relate it to the real world sometimes. So throughout the history of warfare, combat engineers have played a critical supporting role in war efforts. The primary task of the combat engineer is to facilitate the movement of friendly troops and supplies while impeding those of enemy forces. So a combat engineer looks at, okay, where are troops going to move? What do they need to get there? What do I need to build? What obstacles are in the way? And then once we do move, how can I destroy what we use so that the enemies can't use it as well? Probably not as applicable in the warfare of today's time. But anyways, history. As a result, those engineers spend time building structures such as roads and bridges to help move the friendly forces while destroying those that could be used by the enemies. Legend has it that there was a combat engineer who used geometry, surprise, surprise, to devise a way to indirectly measure the distance across a river whose bridge had been destroyed. He devised a way to measure the distance without ever crossing the river or even getting his feet wet. By determining the distance, he was able to devise a plan and construct a bridge with the limited materials they had on hand. So there's some pictures of combat forces crossing the river with their little makeshift bridges in combat. So, what are some distance or lengths that are not easy to measure physically? You can't just go up with your measuring tape and measure it. What are some lengths or distances? Oh, well, yes, circles, but we're not going to be doing circles in our similarity unit. Yes, skyscraper. Yeah. The distance between the sun and the moon. We're going to do that more in our trigonometry unit, not in our similarity unit, but yeah. Here are some of my suggestions. You got my skyscraper one, the distance across a busy highway, the distance across bodies of water. Those are all things that we would want to measure indirectly, not directly. And so we'll just use similar triangles to help us find those distances. All right, so I know you've already seen problems like this in your worksheet, but now we kind of understand why we were drawing those rivers and those triangles in your worksheet. The combat engineer could measure 72. He could measure that by foot. He could measure this by foot. He could measure this by foot. What he can't measure by foot as easily would be that distance across the river. So by using those similar triangles, he could find that distance without ever touching the river. So go ahead and do it. Go ahead and set up a proportion and find the distance across the river. Nothing new here. Didn't want you to approach it any other way. You start however you want. You can start with any of those 4 numbers that you want. I started with 30. So I would say 30 is to 72 as 40 is to x. How do I know which ones go together? Well, I always put the ones across from the vertical angles. I always put those together in the same fraction so that I always know those ones going like perfectly horizontal or perfectly vertical are usually go together. So we cross multiply, and how far is it across that river? How many meters? Good. It is 96 meters. Remember, if it's a word problem, you need to have a word in your answer. You need to have units. So we can be precise. Okay, here's one that we haven't seen yet. This is what my husband does all day, and he told me that this is the real scale factor for a blueprint to the real building or whatever structure. On a blueprint, 1/8 of an inch represents 1 foot. If the height of a wall is 1.5 inches on the blueprint, what is the real height of the wall in the building? So let's find out how tall the wall is. Let's see if it's even realistic. Maybe that guy drew the blueprint wrong and it's going to be a 5-foot wall and no one can fit in the building. Let's see if it's realistic. Bobbin, don't put answers yet. All right. There's a couple ways you could go about this. You can go about it a scale factor way, or you can go about it a proportion way. Let's start off by doing it the proportion way. I like to say inches is to feet as inches is to feet. That way I stay consistent and I know exactly where to put all of my information. So I have this information here, inches and feet. I'm just going to put that in my proportion. 1/8 was an inch and 1 foot. Then I know that this is 1.5 inches. So I'm not confused about where to put it. I know exactly where to put it because I'm putting inches over feet both times. That pesky mouse, it always lands in a bad spot. Now, you might be able to do this intuitively, and you might not need to set up a proportion, but this is for people who don't know where to start, okay? So you would cross multiply. The Hobbit could fit in my 5-foot building. 1.5 times 1, which is, of course, 1.5, divided by 1/8. Now, just be careful. When you're dividing by 1/8, you have to put parentheses around that fraction. You have to protect the fraction, okay? Those parentheses protect it. And you were totally correct. It's a 12-foot high ceiling. That's pretty realistic, right? So that's a tall enough room for most people. Okay, let's try this one. Cut me off in about probably 5 minutes to take your quiz. A 6-foot tall Lewis is standing 18 feet away from the base of a tree. Lewis is shorter than the tree and casts a 3-foot shadow. If their shadows end at the same point, how tall is the tree? I'm not worried about you setting up a proportion. I'm not worried about you cross-multiplying. I'm worried about whether you can draw a picture of this. So take some time. I'm going to pause it. Take some time and draw a picture of that situation. Go. All right, so let's start sketching a picture. 6 feet tall Lewis. I'm not going to draw a stick figure, but if you want to draw a stick figure, you can. So there's going to be my Lewis. He's 6 feet tall. He's standing 18 feet away from the base of the tree, and he's shorter than the tree. So we need to be careful there. So he's 18 feet away from the base of a tree. 18 feet. He's shorter than the tree, so I made sure to draw the tree taller than him. He casts a 3-foot shadow. So he casts a 3-foot shadow. So I'm going to pretend the sun is up here. There we go. If their shadows end at the same point, I have to be careful here. Sorry. There we go. Their shadows end at the same point. There you go. How tall is the tree? So really, you're just sketching a triangle inside a triangle. Yours could have been flipped and going the other way or going the same way as mine. It doesn't matter. You should have a triangle inside the triangle where this segment is Lewis and this segment is the tree. They're going to be parallel because we're assuming the tree is not leaning and Lewis is not leaning. They're both perpendicular to the ground. So we do know that these are parallel. All right, so now we just need to find x. Drawing the picture is the hardest part. Setting up the proportion is not so bad. 3 is to 21 as 6 is to x. Where did I get the 21? I added 3 and 18. Aaliyah, Lewis can be facing either way. He can be facing the tree or facing away from the tree. The way he's facing doesn't matter. Whether I stand this way or this way, it's where the sun is. My shadow is going to fall in the same spot. Oh, thank you, Anas. Is everyone okay with my 21 that I added those together? Is everyone okay with my proportion? 6 times 21 divided by 3. X is 42. That tree is 42 feet tall. Yes, we put units because, yes, it's a word problem. Yes, we need units. Okay? Moving on. Mark is 6 feet tall, but in his Facebook photo, he's only 4 inches tall. What's the scale factor of his Facebook photo to his actual height? Scale factor is different than just finding a missing value. Scale factor is different. Remember, when you're solving, like on today's quiz, when you're solving for x, I don't care if you put first over second or second over first. But when it says find the scale factor, I do care. It has to be second over first. So that's the only time that the order matters here. From his Facebook photo to his actual height. So his Facebook photo is first. His actual height is second. So we want to put his actual height second over first. His actual height over his Facebook photo. Second over first. Now, when you're cross multiplying, notice in this problem, did we change our units? Did we convert everything to inches? No. Did we convert everything to feet? No. Because we were cross-multiplying and the inches canceled and we were left with feet. Now, in a scale factor problem, we are not cross-multiplying. So we can't just reduce this and say, oh, 3/2 is the answer. We have to be in the same units because we are just reducing a fraction. We're not cross-multiplying. So I want to convert both of these to inches because I want my units to cancel. What is 6 feet in inches? 6 feet in inches, 6 times 12, 72. You thought the 6 was first. No, it says his Facebook photo to his actual height. So whatever's listed first is first, and whatever's listed second is second. Facebook to height. Facebook is first, height is second. All right, so let's do it. 72 divided by 4. The units will cancel, and the scale factor is 18. Scale factors are unitless. Scale factors do not have units. They're unitless. Okay? I need you to go ahead and start your quiz.